Okay, close this one. All right. Yesterday we left off. All right. I described what the boundary layer is. All right. Is that what's happening here? Okay. Don't worry, I'll come back to here. All right. So boundary layer, normally the plate's like this. Okay. We have free stream velocity coming in here. All right. Initially, you lose as you progress along the plate. You lose momentum. Hey, settle down, please. Okay. So you lose momentum. So initially you lose a little bit. Okay. You only lose a little bit, and later on you lose a lot more. Okay. So there the boundary layer is growing like this. Okay. This is del. All right. This height del. Okay. Del at y equals to 0, your u equals to 0. At y equals to del, your u is more or less u infinity, or 0.99 u infinity. Okay, more or less there lah. Okay, this is u infinity coming in. All right, so that's what's happening, and the process is because the fluid has a mu is not 0. Okay, so as the fluid flows over the plate, over a stationary plate, all right, there is shearing between the fluid and the plate. All right, that shearing results in loss of momentum from the fluid to the plate. Okay, and that translates to loss of energy, and that energy goes to heat and so on. All right, but that's what's happening here. Okay, so loss of energy from the fluid to the plate because of the shearing. Okay, so that was the main idea that we had yesterday. Is that okay with you? All right, so there's two things we did so far. Del, which is the boundary height, the momentum thickness, not momentum, the boundary layer thickness del, and del star is equivalent to like the blockage. All right. Okay, the real flow is like this. The imaginary flow is like this. Okay, with a block. Okay, imaginary. All right, we say here between 0 to del, here between 0 to del. This one is del star. Okay, we're saying Q of this one, real, is equal to Q of the imaginary. All right, so, and then therefore what is the del star? In other words, the del star is instead of having a funny profile like this, all right, the imaginary case is you have a uniform profile and a block region. What is the height of that block region? Okay, of course, this imaginary doesn't really happen. It happen in your dreams, but normally it doesn't happen. So it's just a concept. Okay, so save. Is that okay so far? All right. So yesterday we had these two. We assume these two velocity profiles. Okay, they are approximate to within 10 or 20%. All right, the exact one is very hard to work with. Okay, so we have this, and if we were to put this in to this, let's see what happens. Okay, so we can actually work out what del star is as a function of del. All right. So if we put in, let's see here. Which one you want to do? You can do both of the. I'll do one. You can do the other one for homework. All right. So which one you want? This one or this one? First one. Okay. Request is for do this one. All right. This one we do now. This one you do homework. So you put this one into there. So can I say? Okay. Put this here. This one, and you okay. So if you put this one in here, what do we get? This is u infinity actually. Sorry, yeah. So del star is equal to 0 to del 1 minus. You put this one here, the u infinity will cancel out. You just get straight away sine pi over 2 y over del dy. Is that okay? So hope you haven't forgotten how to integrate. Del star is equal to 1 becomes y, sine becomes plus cos pi over 2 y over del, here 2 del over pi. Is that correct? Okay, so if you integrate cos, you get minus sine, and you multiply pi over 2 del, pi over 2 del, you should cancel out. Okay, so if you try, if you differentiate this one, you should get back that one. Okay, sometimes for some of you, differentiation easier than integration, so you know, if you want to check, just check differentiate. So if you put del, let's see. Okay, so y del you get equals del plus 2 del over pi cos pi over 2 del over del minus 0 plus 2 del over pi cos pi over 2 0 over del. Okay, so the first part, this is equal to, this one is del, cos del over del is 1, cos pi over 2 is what? 0, so nothing left already, so this is just del. Minus, second one is 0, don't worry about that. 2 del over pi. Cos 0 is what? So, minus 2 del over pi. Alright, which is equal to del 1 minus 2 over pi. What is 1 minus 2 over pi? Punch your calculator. You can try to do it in your head, but unless you like the Rain Man or something like that. It should be equals to 0.36 there, correct or not? Alright? Okay? If you were to do with the parabolic profile, alright, redo with u equals to u infinity 2 y over del minus y squared over del. Alright, dot 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 dot, you would get del star is equal to 0.33 del. Okay, there's slight difference between the two profiles. Alright, this one, homework. Okay, practice your integration a bit. Okay. Okay. Alright, so you want, it's just a parabolic, integrating a parabolic. If you cannot do that by now, bit of a problem. Alright, so I assume you can do it, you should get this one. Alright, so basically for laminar profile, the del star is about somewhere between 33 and 36% of the del. Alright, that's the blockage. Okay, not? Alright, so as the del grows, so does the del star. Alright, the del is growing up. Okay, so the del is growing as a function of x. Okay, I will show you. Alright, okay, so that part is the easy part. Let's now do the hard part. Quite easy, yeah? Okay, the hard part is we want to find skin friction drag and del and so on. Okay, so this is the more complicated one. Alright, is that okay so far? So for the plate, this is the distance x from the leading edge. Alright, here x equals to 0. At the trailing edge, maybe x equals to L, big L. Alright, so x is a variable, being the distance from the leading edge. Is that okay? Alright. Alright, so this is our del, okay, which is a function of x. Alright, at each point you get a different value of del. Alright, okay, if we have here, this is the boundary layer that looks like this. Okay, if we were to draw to follow a streamline, okay, say let's say this position x we want to consider, x equals to something, all right. If you were to draw a streamline, that will go something like this, okay. If I were to draw other streamlines, they will go something like this, all right. This will be the other streamlines, okay. This will be the streamlines. They have to go around the plate, all right, and they tend to fatten up a little bit also because of the boundary layer. But my drawing not so good, okay. So that's how the streamline goes. Is that okay? So streamline means at this point, let's consider this streamline. The velocity is all okay. Now the velocity is always normal to the streamline. All right. If I were to draw a control volume, all right. Before I draw control volume, is that okay? This dotted line is the del. That's the boundary layer. It grows, all right, from 0. The streamline is the line parallel to the flow at every point, all right. So and that approximates something like that. Okay, they're not the same line. This del and this streamline, they're not parallel to each other. There's no bit of fluid that just follows this del line. Okay, all right. So if I were to draw a control volume, all right, between the plate and the streamline, okay, and I call this distance h. All right, I can apply 3 things which I already know. Okay, number 1, what goes inside here is uniform flow, must come out here, conservation of mass. All right, number 2, momentum equation can be applied on this control volume, and number 3, the velocity gradient at the wall is equal to the wall shear stress. Okay, so again, I will write this down in equation form, but we won't solve it, okay? Because it's quite painful. All right, if you like to do it on your own, you can. I think they will do in 3rd year for those doing mechanical. All right, so m dot out minus m dot in equals to 0. M dot out is integral between 0 to del rho v or rho u dA. All right, you can do the u dot n. All right, okay. All right, but dA, but this actually is yes, the black and the blue color lines are streamlined. I'm choosing the black color streamline to do the analysis. Okay, the black and blue are all streamlines. All right, minus, here, easy, rho h times maybe into the page, so rho a times the u infinity equals to 0. All right, this is rho, this is area, h times v. V is the depth into the page, u infinity equals 0. All right, coming in uniform flow can do like this, going out non-uniform flow have to do like this. To simplify, all right, this one 0 to del rho u, which is a function of y, b dA minus rho h b u infinity equals to 0. All right, that's equation number 1. All right, okay, so far unknowns, we got one unknown so far, h is an unknown. All right, we can solve through this equation actually. But so you can put a velocity profile in here and solve for h if you wanted to. So I actually can do that. All right, okay so far. Here, second one, M dot out, V out minus M. Oh, what happened? M dot in, V in is equal to sum of forces. We are doing in the X direction now. Okay? M dot out, V out is integral 0 to del rho uy this one doesn't come dA anymore, it comes dy b dy. All right, so this is rho VA multiplied by B. Okay now, right? Rho VA is your M dot multiplied by B. All right. Okay, just written rho VA multiplied by B. All right. Minus rho H B U infinity. This is your M dot in. Okay or not? Rho AB multiplied by B. By this case, you will be constant, so easy. Equals 0 to X. Here again dA, but I can say B times dx. Alright? This is the shear stress multiplied by area. But the shear stress is changing. Not, so the you want to multiply shear stress, multiply area, B is the width into the page, that into the page, dx. Integrate from 0 to x. Okay? Is that alright? Okay, that's the equation number 2. As I said, I won't try to solve it. Equation number 2. So the second unknown here, this one, shear stress of x. Alright? Shear stress at a particular location. Because that's the area. B times dx is the area. B is the depth into the page. So that's all time the area is the B times. Actually the B will cancel out. Alright? But the B is the depth into the page. So the area is B times dy. Alright? Here is this times B. And here the shear stress is shear stress. The force is shear stress times area. Okay? Actually it's a minus here. Alright? Depends. Okay, but why? If you assume that this shear stress is a positive value, alright? Why? Because this shear stress is acting backwards like this. Okay or not? It's shearing the flow. The flow is going over the plate. The shear stress is shearing it in the opposite direction, slowing it down. Okay? If you shear pushing in the forward direction, then you speed up the flow. That's not likely to happen, so it's going that way. Okay? So that's the only force. Because no pressure force, because pressure atmospheric everywhere, external flow. Gravity force, neglect, viscous force. For outside here, can neglect. Here is outside the boundary layer. This part here. Yeah. This part here, there's no shearing. The only shear stress part is here. So that's the only force. Okay? And the third equation is du on dy at y equals to 0 is equal to shear stress. Okay. Mu times this creature equal to shear. I'll write it the other way around. Shear stress at location x equals to this one. Because the velocity profile, this is equation number 3. Alright? So the third, so you got 3 unknown now. H, shear stress, mu, dy. Alright? So there's another unknown. Oh, the other unknown, I forgot. The other unknown in here is del, which is also a function of x. Okay or not? So there are three unknowns. Alright? In these three equations, there are three unknowns. Alright? Del is unknown, although we say we interpret to del, but we don't know where del is. So there are three unknowns and there are three equations. So by that I can solve that. But it's quite painful. Okay? So for this unit, you won't solve it. You just need to know that this is how I got the equations. Alright? The first one is conservation of mass. Second one, conservation of momentum. Third one is just your velocity gradient, u dy is mu, shear stress. This is basically your shear stress at the wall. Alright? The velocity gradient at the wall, multiplied by this is your shear stress at the wall. Okay? So right at the wall, number 3, what's happening is, right at the wall, you got your velocity gradient. Okay? So this point here, this gradient here, that's your du over dy. That is your shear stress. Okay? Actually, there could be a minus sign here also. Alright? Because again, your fluid, your du dy is positive. There is positive increase in u as a function of y. So du dy is positive. U is positive, but your wall is being sheared this way. Okay? While the fluid is shearing the wall this way, the fluid is shearing the wall this way, the wall is shearing the fluid this way. Okay? So actually, wall on fluid is actually this way. Alright? And since all our equations are shear stress x is wall on fluid, so it should be minus. Okay? So those are the three equations we won't solve. But are you okay with it? Alright, so if you're okay, I understand what? So somehow you put all that in and then you let someone else solve it. I believe we have an expression for del over x equals, and we have expression of CDF. Okay? Right? So do a solve. Dot, and you get this one. Alright? These are the two things we wanted. We wanted to know how the del changes with x, how the boundary layer grows. And I think the answer is, I collect here. Don't worry, you don't need to memorize the answer, it's on your formula sheet also. Okay, let's skip all this. Okay. No, before. Alright, del over x is 5 over square root rex. 5 over square root rex. Alright, in this case, rex is equal to, it's a non-dimensionalized parameter with respect to x, is equal to rho vx over mu. Alright or not? Okay? So, and your CDF, which is depending which profile you use, the number is a little bit different. 1.31 or 1.46. 1.31 or 1.46 square root of rex. Is that right? Yes. All right. There's an example here also. Okay. So this CDF, I don't know why the notes didn't tell you what the CDF is. Detail. CDF, all right, is equal to the F skin friction over, all right, half rho V squared times B times L. Alright. Actually, by right, this should be REL. Alright, where REL is equal to rho VL over mu. Okay? This skin friction, alright, is actually that picture up there, number 2. Okay? This one is equal to this one. This F skin friction. Alright? So that's the total force on the skin. Is that right? Okay? So if you want, we can do an example. Alright? Okay, let's say air. You want air or water? Water. Okay, water. Alright? Water, the density is 998. The viscosity is what? 1.2 by 10 to the minus 3. Is that right? Okay? I think so. You know, you check. Okay? 1.2 by 10. Okay. So, I told you the formula is here. Where is the formula? Where you don't have? Huh? Huh? Don't have. I thought God, but don't worry. If you need, they will put it in. Don't need to memorize on. Some years got, some years don't have. Okay? I don't know if you want changing the formula sheet. Alright. Okay, so let's assume water. And there's a plate. Okay? There's a plate here. Say the length. Say 3 meters. Okay? The depth into the page, L equals 3 meters. The B, just put there 1 meter. Okay? What we want to find is del at 1.5 meters and 3 meters. Boundary layer thickness at 1.5, 3 meters. We want to find CDF for one side. Okay? For one side of the plate. Right? You guys sometimes want to ask me on the other side. Okay? Some of you don't know, please consider both sides. Right? For this one side. Okay? So first, we use this formula. Okay, for this formula, let's say at 1.5 meters, del over 1.5 is equal to 5 over square root of rho 998 v. Oh, I didn't tell you what the velocity is. 2 meters per second, I say. Rho v x 1.5 over mu is what? 1.2 by 10 to the minus 3. Alright, what is del? Is that okay? Second one, at 3 meters, same thing. So, okay, but only thing I need to change 1.5 to 3 meters. And del equals to, alright? It's very thin. Alright? Few mm only. Okay, I expect the answer few mm. Is that okay? So you can predict the boundary layer thickness. Alright? And if you want, you can also predict del star. Del star is equal to, say, approximately 0.33 del equals to what? Okay? Huh? What is x? X is the distance up. If you're 1.5 meters from the leading edge, x is 1.5. If you're 3 meters from the leading edge, right the edge, then x is 3. Right? Okay now. You want to calculate answer? What's the answer? Huh? 0.047. So that's about 4.7 mm. Okay? That's very small. Second one? Okay? While some of your friends are calculating away, we can do the next one. Alright? So, you can use either one. 1.31 or 1.46. I use 1.31. Huh? The difference is this one is for, I think the sinusoidal profile, this for the parabolic profile. Okay. Huh? Parabolic, I think it's this one. Alright? But I just use 1.31. Okay? CDF, which is equal to F drag over half rho V infinity, half rho V squared B times L is equal to 1.31 over square root of RE x square root of 998, actually the same one there, 2, 3 over 1.2 by 10 to the minus. Alright? Okay? What's the answer for the second one? What's the answer for the at 3 meters? Huh? 6 point mm. Okay? Alright, so the skin friction drag in this case, F skin drag over half, rho is 998, U is 2 squared, B is 1, L is 3, is equal to 1.31 over 998, 2, 3, 1.2 times 10 to the minus 3 equals, therefore, F skin drag equals how many newtons? Alright? Also will be quite small. Alright? Skin friction drag normally quite small. Alright.
So we can take 1.5 also.
You can take the other one also. Alright? Depends. Don't try to remember this number. If a question comes out like this in the exam, they will provide you with the data. You use the one that provided. Okay? I think the older formula sheet used to have, then I think they take it out, then I don't know, sometimes they put it back in. Alright? So, if it's in the formula sheet, use that number. If it's in the question provide you with the number, say laminar flow, you use that number. Alright? What's the answer? Huh? .5 newtons. All agree? Okay. Alright, quite small. Okay. So is that okay? Alright, draw a line. So the remaining part of this lecture, we talk about turbulence. Okay, so Here Rex is rho Vx over mu. Alright? Uniform flow coming in. Alright? So, and this is your boundary layer. This is x. So here x is 0. X equals 0. Alright, so you expect your Re x equals 0. Okay? The Reynolds number is a ratio of inertia over viscous. Okay now? Alright? It's more or less inertia over viscous. Alright now? Okay? So when Rex is 0, alright? Basically this is very much bigger than this. Alright? So for Re, low Re, your viscous is much larger than your inertia. Alright? And that happens in this case close to leading edge. Is that okay? Alright? So for small Re0 or Re small, your viscous is much bigger than inertia, that's why you get a small number. Okay? Or at least your viscous dominates over inertia, you get a small Re. Okay? And that's why, then this one, in this case, when viscous dominates, you get laminar flow. Why? Because there will always be disturbances. There will always be deviance. Alright? There will always be some noise, there's some disturbance, some foreign molecule, not quite water going there, some roughness of the plate and so on. Okay? So there will always be some disturbance. When this happens, in this case, your viscous forces is like glue. Okay now? Think of it, high viscous fluid is like oil, like very sticky like that. So it will dampen out. Is that okay? So high viscous fluid will dampen out any disturbance that you might have. Therefore, continue to maintain it laminar. Alright? Okay? But at some certain point, alright, for this plate, at some high Re, what is high later, we'll talk about it. High Re, your inertia will start going more than your viscous. Alright? Alright? Where x starts to be, either x starts to increase, or v starts to increase, or mu starts to go down, whichever the combination for you to get the high Reynolds number. Alright? Then what happens is we get what you call turbulent flow. Alright? Okay? And in most cases, a lot of cases, the flow will become turbulent because Reynolds number normally is very big. Okay? But why it becomes turbulent is, as I said, there's always okay, so this again is applicable to other situations, but we'll do it for the boundary layer since we are talking about that now. Alright, so here is laminar. Here your Rex starts to become very big. Okay, you have a nice big boundary layer like this. Okay, what's happening is, again, there will be disturbances. There will be either noise or upstream, right? People talking at the back of the class, whatever. There will be some disturbance. Okay. With this case, when you have disturbance, your inertia dominates. So your viscous, the glue doesn't hold it together anymore. So once one fella start going down here, okay, because of continuity, one fella must go up also. Okay, now, all right. So the flow will start to break down into a lot of so turbulence. All right, one characteristic of turbulence is you have a lot of scales. All right, not just one scale. Like in the lab flow visualization we did, that's not really turbulence. That's not turbulence because we only saw the eddies or the swirls, the vortices are about the same size. Alright? There's two sizes actually. One that roll off at the shear layer, alright, the boundary layer, shear layer rolling up, the little ones, and the big ones from the wake. Okay? But turbulence is not just about one or two sizes, there must be a whole range of sizes. So initially, you have some breakdown of your order or the structure. Okay, so it's not laminar anymore. It breaks down, and when it starts to break down, what happens? Okay, so they will interfere with each other. Okay, so initially you form one size, and then after that, this size will interfere with another one of this size, and then they'll break down. They'll form smaller and smaller, and so on. Okay, until very small, then your viscous effects will dampen that out. Okay, so the viscous effects will dominate for the small one because the local RE equals rho V L over mu. This L of this size becomes very small. Okay, that's so it will dampen out. So it cannot go. It doesn't go down to the microscopic scale and nanoscopic scale. Okay, there's unlikely to have turbulent eddies down that size. There will be some cutoff range. Okay, but basically turbulence is that thing, and it also is 3D. Not all of them are just tubes coming out of the page like this. The tubes, the rollers will be in all different directions. Okay, so that's turbulence. All right, so turbulence. Okay, number one, RE must be high. What is high depends on the particular situation. For pipe flow, there's a transition where it goes from laminar to turbulent. For this one, there's also a transition number, and that number is different. So for each case, that number is different, but generally it's high. All right, a higher Reynolds number. Okay, turbulence, you get high Reynolds number, you get length scales, variety of length scales. Okay, what else? RE high, variety of length scales is normally 3D. All right, so 3D with vortex tubes in all directions. Okay, so they'll turn here, there, and so on. I got a picture. I don't know, save. Whether you got. Okay, so there, this picture of turbulence. Not a very good picture, a very old picture. Alright, so you can see, alright, this is the top view, this is the side view. Alright, this smoke visualization of over a boundary layer. Okay, boundary layer here. You can see at the start, from the top, all the smoke trails are going more or less straight. Correct or not? Alright, here, smoke trail going more or less straight from the top view. From the side view, you can't see anything lah. So on top view is going more or less straight. That's the laminar part. Okay? Then after that, there's a lot of vortices. Alright? It breaks down. There's some big ones and there's some smaller ones here also. So this is the side view. Some big vortices, smaller vortices, and so on. Okay? So the smoke, not very clear, but you can see lah. Okay, there's some big ones. Alright, some small ones. Okay? From the top view, you can see, so it's 3D, so these vortices are not just this way, so this is just a slice of the thing. Alright, they also, okay, so besides going around here and here and here, alright, they also go round in the top, if you look on the top, so there's a lot of mixing. Okay, so that's turbulent flow. Alright, okay, so again, there are a lot of other examples of turbulent flow. Alright, okay, so this is one of them. We'll look at other pictures later. Alright, for pipe flow and so on. Okay, okay, so this is what actually happens in for boundary layer. This is a schematic of it. We have a laminar part, a transition, where you get some characteristics of laminar, some characteristics of turbulent. state or sporadic turbulence, you want to call that, okay, before it becomes fully turbulent. Alright? So factors affecting it: upstream velocity, yes, that affects your Reynolds number; distance along the plate, that affects your Reynolds number; the roughness of the surface, okay, if it's rough, that gives a more instability to kick off the turbulence. Alright? If there's any disturbance or turbulence from upstream before it reaches the plate, that will also instigate the turbulence. Fluid properties, if it's not uniform, that will instigate turbulence. Pressure gradient or absence of this one no worry first, we'll talk about it. Okay? That one we'll talk a lot more about pressure gradient, so don't panic about that one first. Okay? So for a plate, the transition occurs at about 5 Reynolds number, RE based on X of 500,000. Alright? 500,000, but it can go as low as 200,000 and can go as high as 3 million. It's basically how this number varies because of the other factors that I talked about. Upstream turbulence, other disturbance, people talking at the back of the class, maybe your building shaking, alright? All those things will affect it. Okay? If you're on top of a very tall building, there is a bit of shaking. Okay? Alright, so if you are very stable, you can push it up very high. If you're very noisy, very bad, very crude and all that, rough things and so on, then it will go down. But typical value for this and all our analysis, we use 500,000. Okay? 5 by 10 to the 500,000. Right? So later we'll do pipe flow. So this number is only for this particular problem. Different problem have different number. Because that number is specific to the problem. For pipe flow, the transition range is between 2,100 to 4,000. So in other words, below 2,000, laminar flow. Above 4,000, turbulent flow. In between, you got some transition. Alright? So this number, don't just burn in your head, bite on your shoe, whatever it's like that. That's only for this particular case. Alright? So, okay. Next week talk about turbulent profile. Alright? Before I talk about this one, close this one. Okay? So turbulent. Okay, so for one, turbulent has a lot of eddies going up and down. Okay? So previously, if your profile was laminar, it was like that. Okay? But what? You add this plus this, okay? Laminar flow or your laminar profile plus turbulence, what do you get? What you end up is, you get a lot of mixing. Previously, the flow was like layers. Okay, no? Like layer cake, laminar, laminate flooring, like layer one. Okay? So, like layer cake, alright? Then you add all these deviants, this flow, some going up, some going down, some going into the page, some going out of the page. Alright? What that tends to do is mix up all the flow. Okay? So when you mix up all the flow, what happens is you get a very steep. Alright, this is very hard to draw because it's actually very thin. Okay? It's actually very thin. This also over exaggerated. If just now we had like 4 mm, this one might be less 1 mm or less. Okay, just now equivalent. Now we're calculating 4 or 6 or whatever mm. This one may be even less than 1 mm. Sometimes you can go all the way down to the surface roughness of the plate. So your roughness elements, few molecules sticking up, the boundary layer to be on that. Okay? So that's the turbulent boundary layer. Okay? So straight away you can already realize, well, here your du on dy is low. Here your du on dy is very high. Why not? You have a sudden change in velocity. Alright? Here you have gradual change here at the wall. Here you have very sudden change before it becomes uniform. Why not? So you expect here high wall shear stress. high wall shear stress. Alright, and what else? And therefore, high skin friction. Okay, no? Okay, so it's high skin friction. So with turbulent boundary layer, alright, because of the turbulence mixing all the momentum around, you get fast moving fluid near the wall. When you have fast moving fluid near the wall, you get more shearing. More shearing means more stress, more wall shear stress. More wall shear stress means more overall, more higher skin friction drag. Okay? Okay. Is the explanation okay now? Alright? So there the picture here tell you the same story I just told you. Okay. Pipe flow, don't worry about it first. We'll talk about it later. Okay. Alright. So I'll finish off with this slide. Okay. I'll finish off here. So these numbers, okay, for turbulent flow, there's no way to do it analytically. There's no, well, there is, but it's funny. Okay, there's no simple velocity profile for the turbulent flow. All right, so all these values are measured experimentally for turbulent flow. Del over x, del star, and CDF. Okay, so you have to use it. You just use this one. All right, we'll do examples next time on this one. Okay. Quiet, please. One last thing, but I'll repeat it next time also. Since we are the last slide, okay. This value, so this value is for smooth plate, no surface roughness. But for turbulent flow, sometimes the turbulent boundary layer can get so thin that it's of the same size as the roughness of the plate, and therefore all right, this is laminar flow. Alright, you expect turbulent flow higher, so this is turbulent flow, the CDF. Okay, this for smooth plate. But if your plate is not smooth, it has roughness, maybe set like sandpaper or whatever thing, depend on the surface, that polishing and all that, you can get higher. And therefore your skin friction will be higher. Okay, so it does depend on the roughness. But I'll reiterate these two things before we do some examples on Thursday. So I end here. Okay. Those I think need my signature, wait outside in case next class wants to come in. Yeah, that's it.